Good morning, students. Today's topic is B tree. B tree is a balanced MV search tree. You know already what is binary search tree. In binary search tree, we will be having a number of nodes, but every node must have either 0, 1 or 2 children. That's it. We can say at most 2 children. And every node must have only one key. You know already this one. So it will be like a node with 2 children. As you can see, I'm drawing here like this. So here if you have 10 inside, so a 10 is called as a key to that, right? And a node to its left must have a lesser number than 10, that must be less than 10, that is 5 something. And the right node must have an element with 15. How we can say 15? So it must be right subtree must be the highest number than the root, and left subtree must be the lowest number than the root. So this is a search tree. You can see here you are having only 2 children, like at most 2 children, and every node is having only one element, that is 5 is one element, 10 is one element, 15 is one element. But coming to binary search tree, binary tree, so it will be having a number of nodes with, you can see, I will show you this where you can find basic binary tree example over there here. So you can have like this. So here, see, if you take this 78 and 99, there this node is having 2 elements, that is 2 keys, we have to say as 2 keys, 78 and 99. So this type of now, like more than one key you are not seen till now, right? So that you can see in binary, like B trees now. Okay, so this is the first case. And second one is, you can have n number of children. In binary search tree, you must have either 0 or 1 or 2 itself. But in B tree, you can have n number of children depending on the order. Okay, what order? So that is why the definition you can give to a binary tree is balanced MV tree, where M indicates order. Okay, M indicates order. So this order will decide what, like how many keys it must have and how many children it must have. There are several properties to B tree. We are going to see all those now. Okay, before going to that, so let us see where we are applying this B trees. Okay, we are applying this B trees especially in data structures. Okay, we should know the applications first before entering into the topic, right? So we are applying this in the data structures, particularly like databases. So this is one of the data structure which we are using in the databases. So this data structure must be like multi-level indexing type. Here we are showing this multi-level indexing type. So multi-level indicates that, so if I am dependent on person 1, okay, person 1 is dependent on person 2 and person 3, and person 3 again hierarchically this is dependent on person 4. So this is multi-level hierarchy. Everywhere one component is dependent on the other, right? So this scenario we call it as multi-level indexing or else multi-level hierarchy. Why we are saying indexing? Indexing indicates that this number, this ID number, is dependent on person 2. Okay, now person 2 is dependent on person 3. So this is indexing type we have to say, right? So we can take one example. See here, it is applicable when there is need of multi-level indexing data structure. So the best example we took is disk structure. So here in this disk structure is this one. So you can see this disk structure with the tracks. Tracks are what? These are tracks. These are tracks. So round one, so where it is rotating, those are called as tracks. And the part where we are dividing our tracks into some parts, so this part is called as a sector. Okay, this is called as sector. And now a part of your sector and your track, this is track, right? This is a track. So a part of sector and your track, this, so where it is meeting, this is called as a block. We have to say that is also, that is called as a block. So a block definition is what? It is the intersecting part of both track and a sector. Okay, so always this block, consider, let us consider this will be of 512 bytes. So we are mentioning here, right? So whatever we are operating, we must save in our disk, right? So this disk data structure is nothing but B tree, right? So whatever we are reading, whatever we are writing from a disk or into a disk, that is with respect to a block. Are you understanding? Okay, so this block will decide like what to write and how to write, what to read, like accessing part, totally accessing part is dependent on your block. Now block address, how we can say this block address? Block address is nothing but this sector address and your track address, this track address. Okay, so that is called track number, and sector number will decide your block address. Okay, so this is a part of your block address. Why we are discussing this now? So this is the application where we are using our B tree. So how we are using, we will see now. So see here, every block will have 512 bytes of memory, right? And this 512 bytes of memory is from indexing from 0 to 511. Okay, so from 0 to 511, each byte is called as an offset. Okay, so now whatever the data we are saving, that must be saved with respect to the offset value. Okay, so let us take student information as one of the database. So what a student information will be having? Basically his ID, his name, his department, his section, and so marks. So let us take student ID is taking 10 bytes of memory, and student name is taking 50 bytes of memory, and student's department is 10, and student section is 8, and student marks is 50. So totally it is taking 128 bytes for each student. We can say each row. Okay, 128 bytes of memory is needed for each student. So like this, what we have said, every block is of 512 bytes. So how many student records we can save in one block? So that 512 by 128, like number of records per block. So one block is having 4 records, each of 128. Okay, so 128, 128, 128, 128, so total 512. Are you understanding? So 512 by 128 indicates that 4 records. So thus every block contains 4 students record information. So how many 512 bytes means 4 records, right? So like that, if I have more than 100 students information, how many blocks I should need? So we have to calculate it accordingly, right? Every block will be accessed by indexing. Here enters the indexing concept. So before entering into student information, we must know block value, block info. If we know only block info, then we can go to student info there. Okay, so every block will be accessed by indexing. It will be having a unique ID and a pointer. So why pointer? Pointer will be pointing to record, each record. Okay, a unique ID means every student will be having a roll number as a unique ID, right? So that unique ID we will maintain as a table over there. Okay, so see here, I will be explaining this. So how multi-level indexing is there? So this is n number of students information. 1 student, 2, 3, 4, 5, like this. We have 100 records, suppose 100 records. Okay. So just before I have said that 4 records per one block, right? So this block info I am saving in this particular index. So this index is the next version of this, right? First info is this, first one is this. So from here I am generating this, having this information, I am generating this table now. So this is having block info. So each block will be having, each cell like record will be having a block information. Okay, again this block, if the number of records are increasing day by day, okay, like this it is increasing day by day. So this records information we are saving here. Next I am saving here. Next I am saving here. It is going on increasing like this. So I am saving. Now this table is also going on increasing. Again I have to increase this one. Like here one slot will be again analyzing this one. So it is a type like if you have this part is like students, okay, this part is like class reference, okay, this is like section reference, okay, and again if that is also not like able to find out, then again I have to give like a group wise, then I have to give individually. Okay, so like this day by day I am increasing the database so that I am increasing the hierarchy. So how it is been increasing? From top to bottom. Okay, so if you turn to one of the face, so it will be like this, it will be like this. Okay, you can see like this. So this is 100 records of student information. From here block information. Okay, from here again. So like this my indexing is day by day increasing. Okay, so here directly what I am saying, a B tree is self-managed multi-level index. When the size increases, high level index is increasing. So did you got the point? When this size is going on increasing, I am increasing the level of this one also, and then from here I am increasing this also. Okay, so this is a part of multi-level hierarchy. Now, so how this has been like linked to our B tree is a matter. So see here, for this type of database indexing we use B tree. So why B tree? Because B tree is M-way balanced tree. Okay, what is M-way now? M-way indicates the order. Okay, so now we have directly M-way also. We have directly binary search tree also. What is binary search tree? Just now we have discussed. There are no multiple keys. We are saying there are no multiple. If we have a node, we can't insert 10, 20 here. Okay, we should insert only one value called 10. That's it. That is binary search tree. Every node will have only one value and at most 2 children. And every child will have only one value again, 1 5. 1 5 kadu. Why? Because it is like left subtree. So left subtree must have lesser value than the root. 7. Let us take 7. Okay. So this is binary search tree. Next, coming to M-way. M-way indicates that there are no specific properties. There are no specific properties to M-way. We can have like this 10. Okay, we can increase. So like this we can go on increasing. Just here I have given. We have directly M-way and binary search tree, where B tree is combination of M-way, binary search tree and some properties. So let us see. So M-way is like 5, 10, 15, 20, right? So see here, 5 is smaller value than 10. So when I try to insert 10, it must be right subtree because always right subtree must have greater value than the root value. Okay, so 10 is greater value, so I have to insert to the right, and the left side it is empty tree. So left subtree is empty, right? Now again I am inserting 15. 15 is greater than 5 and greater than 10, so to the right of 10. Now 20. 20 indicates greater than 5, greater than 10, greater than 15, so it must be to the right of 20. So like this I am go on increasing the right subtree without having control over the tree, right? So tree, see here, height increases 4 levels, 1, 2, 3, 4 levels of height. If there are n way, then n levels will be a tree. Like n levels, level of the tree will be n over there. So there is no control. That's what we are saying. No control over the height of a tree in m way, not in binary tree. Okay. So to overcome this, binary search tree must have at most 2 children only, and M-way tree is having no control over the height of the tree. So thus to overcome this, we introduced B tree with specific rules. So what are the rules we have? So let us see. These are the properties of your binary tree, B tree. Now B tree is a balanced M-way tree. This is first point. Second one, B tree is binary search tree. Just now we have discussed. It can have more than 2 children and more than 2 keys, right? So just now we have discussed every node may have n number of values in this, right? So this is a first property to say. This is the first property. Next property, if we are saying M-way, M indicates what? Order. Okay, M indicates order. Now B tree must have all leaf nodes at the same level. So just now we have seen M-way. So are the leaf nodes are at same level? No, right? So here all the right subtree is increasing but no left subtree at all, right? So here we must say that all the leaf nodes at same level. We are going to see that. Next, minimum children is dependent on the M value whatever we give. So if M is 4 by 2. Okay. So minimum children will be 2. If M is 5. Okay. 5 by 2. 5 by 2 is nothing but 2.5. There we have to take seal value that is upper bound. So there the value will be 3. Next, minimum keys. Minimum keys, like minimum. How many number of values minimum we have? So 5 by 2 indicates 2.5. So seal value is 3. So 3 minus 1 is 2. Okay. Now maximum children must be M. Maximum children. So how we have to give this is, if my M value is 3. Okay. So here I should have how many keys now? So maximum keys are M minus 1. So M minus 1 means 2 keys only. K1, K2. Okay. And in between I should have this pointer. So pointer indicates how many maximum children we may have. M indicates 3, right? So 3. So left side, middle one and right side. Okay. So this is child 1, child 2, child 3. Okay, again this child must have how many minimum keys? How many minimum keys? Keys are M by 2 minus 1. So 3 3 by 2 is nothing but 1.5, that is 2. 2 minus 1 means minimum we can have 1 value. Maximum are 3 itself directly. It's like 1, 2, 3 our range should be there for children count, children. Okay. Next, it must be grown bottom up. So how we are saying it is bottom up? So we are not designing a tree like this. We are not designing a tree like this. Okay. We are not designing like this. How we are designing? We are designing like this. If we have like this, then we are violating this, and to the upper we are giving this. and to the upper we are giving this. Okay, so like this our like design will be from bottom up, not from root to leaf. This is from leaf to root. Okay, this is very important point to be noted. Next, root may have minimum 2 children, maximum m minus 1 keys. So minimum indicates that if it is like minimum itself is 1, like keys minimum itself is 1, then root may have 1. Okay, but if the minimum is 3 and if the minimum is 5, then it can have 2 also, no problem. Okay. Next, now moving to the operations of B tree. If you can see the operations perfectly, then you can understand what is B tree. So there are 3 operations: insertion, deletion and searching. So insertion, deletion, okay, coming to searching. So searching indicates that just now we have seen. So how it is coming to here, where it is this. If I am supposed to search for 15. So what I have to do? 15, come to the root first. Okay, so root value is 5. Now 15 will be either to the right or to the left subtree. So directly we can say 15 is greater than 5. Thus 15 must be to the right side of your root. Right. So again coming to the next value 10. I will compare 10 with 15. It is not equal. Now what I have to do? I have to check with its, like either it is a greater value or lesser value. I will finalize like 10 is less than 15. So 15 is to the right of 10. So move to the right subtree. So if there are some values here also, we will skip all those because 15 is greater than 10. So I have to move to the right side itself. So like this our searching process will be there, and the complexity is big O of log n. Okay, big O of log n. So here I have written this: searching start from root and compares it. If the value is less than, then move to left subtree or else to the right. Okay, if I am searching for 3, suppose if there is 3 here, suppose if there is 3 here to the left side, if I am supposed to search for 3, so I will compare 5 with 3. So is that equal? No. Then again I have to compare, either it is lesser than 5 or else greater than 5. If it is lesser, I have to move to the left side. If it is greater, I have to move to the right side. That's it. Okay, searching is very simple. Now moving to the insertion. Both insertion and deletion operations must follow the properties of B tree because we have several rules, right? Just now we have mentioned the properties. So these are the some of the properties. These, okay, all these properties we should not violate while inserting or while deleting the elements. Okay, now we are moving to the insertion part. In insertion, see here m-way B tree. Let us consider 3. Okay, m indicates like m equal to 3 over there. 3 is the order. Now maximum number of keys formula. What is the formula for maximum keys? m minus 1. So see here, maximum keys are m minus 1. Maximum children are m. So that's what we have written over there. These 4 points we have to write first itself. Okay, minimum are nothing but 3 by 2 minus 1. So ceiling value is nothing but 1.5. The value will be 1.5. Upper bound is 2. 2 minus 1 is 1. Okay. Next, minimum children are 3 by 2. 1.5. Upper value is 2. So children are 2 minimum. Maximum it may have how many children? 3 children. Minimum are 2. Coming to the values, minimum we should have 1. Maximum it may have 2. Okay. Now I am trying to insert the values from 1 to 10. Okay, 1 to 10. Now insert 1. Okay, now I am trying to insert 1. So as there is no values, first I have to check either it is an empty tree or else do I have any values. Okay, if it is empty tree, directly insert with a node with 2 slots. Why 2 slots? Because I can have maximum keys as 2, right? So that is why I have given 2 slots over there. One slot is for one value and other slot is for other value. Okay, insert 2. So without going to the child part, here itself I have inserted 2 because I have a slot for the other value, right? Next, insert 3. Insert 3. Now, can we insert 3 like this? 1, 2, 3? No, because what is the condition over there? What is the condition over there? The condition is maximum keys I can give is only 2. I can't give 3 like this. 1, 1, 2, 3. I can't give like that. So that is violating the rule over there. Immediately I have to take another step. So from bottom to the up. So what I have to do? I have to 3 is greater than 2, right? So this must be 3 must be to the right side and 2 must be the parent now. Okay, so that's what we have done in this step. 2 went to the as a root, and to the left we have 1, to the right we have 3. Now check the condition of BST. Like BST is nothing but binary search tree. Root value must be greater than the left, and the root value must be lesser than the right. Is that true? Yes. 1 is lesser than 2, so left subtree succeeded. Next, 3 is greater than 2, yes, right subtree succeeded. So okay, this we, for every step we have to analyze the number of keys, the number of children, and BST rules, that is left and right subtree parts. Okay, now insert 4. So where 4 should be? 4 should be compare with the root. 4 is greater than 2, right? So it has to move to the right side. So do we have a slot here? Yes, after 3. Yes, right? So insert here. Now I am trying to insert 5 now. So while I try to insert 5, so can we insert like this by keeping extra slot? No, that is wrong, because the maximum keys I should have is 2 only, right? So now this 5, to insert this 5, I am making this 4 to be a root now. Okay, and I am inserting 5 here. So before inserting 5, check this step now, this step. 2 as it is, 4 it has been moved to the upper, so it has 4. Next, 2 is greater than 1, so it is correct. Now, do we have 3 between 2 and 4? Yes, right? So here we should have a pointer now. This pointer is pointing to the 3. Here we should have a pointer pointing to the left subtree of 2. Here we should have a pointer pointing to the right subtree of 4. So check the conditions now. 2 as a root, left subtree is lesser, right subtree is greater. Now 4 as a root, left subtree is 3, is lesser than 4, yes. Next, right subtree of 4 is 5. So is that true? Yes. So everything is okay. Now come to insert 6. So after 5 we have slot free, insert 6. Okay, next to 7. So while inserting 7, again a problem. What happened? Here we can't insert, right? Because only 2. Now what I have to do? 6 I have to send to the root, and I have inserted 7. Now what happens? Where I have to, coming to the parent part, already it has been with 2 keys. Now where I have to insert this 6 now? Again a problem, right? So among these 3, I have to send 1 to the upper again. So that is a resultant tree here. So 4 has been moved to the top root. Next, 2 and 4 as a left and right subtrees, and to that obviously just before whatever we have. Check now. So root, as a root, 4 has all the values less than 4 itself, or else not. Check it. 2 is less than, 1 is less than, and 3 is less than. Next, 4 right part, all the keys are greater than 4 or else or not. Yes, 5 is greater than, 6 is greater, 7 is greater, right? So like this we are increasing the level to the up, right? So just before it is only one level here it is only one level. It has been increased to second. Indexing, this is called as indexing. If the values are increasing, okay, we are go on increasing our level from bottom to the up. Okay, are you analyzing this? Yes. Okay, so like this, 7 inserted, now 8 inserted here. Now while inserting 9, a problem with 3 elements again, so move 8 to the upper layer directly. Okay, so like this we have to insert the values. Now coming to the deletion part, same part. So what? Without violating the properties, we should delete an element. Now see, delete 19. So consider this as a tree. I have just written like that. So delete 19. So if I am trying to delete 19, is there any problem? No, because if I this is a leaf node deletion doesn't have that much problem, and it has minimum one value because it is three-way. This is three-way. Okay, three-way because we have maximum 2, okay, and maximum 3 children, right? Two keys, 3 children. You can, by saying only we can say, okay, 3 children, right? So this is three-way tree. Now delete 19. 19 is a leaf node, right? It doesn't have any child. Next, if we want to remove 19 key, search for it first. So how to search for it first? 19, come to the root. So 19 is compared with 17. Is that lesser or greater? If it is lesser, move to the left. If it is greater, move to the right. Right. So 19 is greater than 17, right? So move to the right subtree. So come into here. 37, 51. So 19 is not lying between 37 and 51. So it must be less than 37 itself, right? So come into the left subtree of 37. So 18, 19. So we have found 19 as a value, delete it directly. Okay. So found 19, delete it because it is not violating B-tree property. So if we delete 19 also, no problem. 18 will be like that only. 39, everything will be, the remaining tree is like that itself. Next, delete 39 now. So coming to deleting 39. So can a node be empty? No, right? So if the case is like this, okay, if the case is like this, see here, leaf node but single key only, then merge must be happen. What is merge now? So merge indicates that either from left sibling or from right sibling. Siblings are nothing but immediate to the left and immediate to the right, not parent, okay, immediate to the left and immediate to the right. So here immediate to the left we have only 18. This is again single, so we are not going to touch this. And immediate to the right we have 2 elements. Okay, we have scope here. Okay, so from here what I am doing is, before deleting 39, I am bringing 51 down and I am taking 78 up. Okay, 78 up. See here, resultant tree is like this. 17 is as usual, left subtree is as usual, right subtree change is happening here. Check it. See, 37, it is like this itself. Now what I have did, 78 I have moved to the upper one. So see here, 51 is replaced with 78, and where 51 is in place of deleted value. Okay, now deleted 39 without any violating the rule. Okay, so that's it. So again check it. So 37 value 18 is less than 37. Yes. 37, 78 mediator value is 51. Yes. 78 is less than 99. Yes. So every rule is okay, and the keys, minimum keys and everything is fine. Now delete 51. So if we are going to delete 51 now, okay, if I am searching for 51, okay, left sibling is having only one value and right sibling is having only one value. So what should the scope to merge now? No, right? Now I have to find the solution with the parent. Okay, there are 3 scenarios I am showing you. First one is directly deleting the leaf without any other effects. Okay, coming to second one, delete 39, but one of the sibling is not free and one of the sibling is having maximum keys. So there we have one solution from the siblings. Okay, last one is there is no solution from siblings at all. Okay, now I have to find the solution with the root, directly with its parent. So what I have done, 17 as usual, left subtree as usual. Okay, coming to here. So 37, what I am doing here is I am deleting a node totally. Okay, I am deleting a node totally, right? So what I am doing, 37 I am bringing down. Okay, I am deleting 51 directly. Just I am doing 37 I am bringing down. Okay, 78 as a root itself and 99 as a right subtree itself. So check it here. Okay, 78, 1837, and check your values also here. So 1837 is greater than less than your 78 value, and 99 is greater than your 78 value. So like this, while deleting and while inserting the values, we have to check these scenarios everywhere without violating the properties. Okay, so this is properties and what is like where we are using B trees data structure. So it is specially used in disk databases, so where the data is going to be increased in future for like many records, there we are using this. Directly we have to say multi-level indexing. Where multi-level indexing happens, there we have to use B tree concepts. Okay, done with B tree. All the very best. Sign off.